Derivative of tan x. So let's figure out the derivative of tan x. So we'll make use of first principle of derivative. So what is it? How does it look like? We have limit f of x plus h minus f of x, not h. This entire thing divided by h as h tends towards 0. That is your f prime of x. Now, I always advise, let's take up f of x plus h separately, simplify that and then substitute it back. So this would be tan of x plus h, and this is nothing but tan x plus tan h, and this entire expression divided with 1 minus tan of x into tan of h. And now what do we do with this? Substitute it onto 1. Substitute in 1. So we have f prime of x is equal to limit h tend towards 0, and then we have, just a second, tan of x plus tan of h, this entire expression divided with 1 minus tan of x into tan of h, and we have minus tan of x. That's your f of x. Agree? There's something else missing, divided by h. So I'm going to write it as into 1 by h. Is that correct? So let me explain it in this way. Say we have 2 by 3. I can write 2 by 3 as 2 into 1 by 3. That's all I've done. Now, so further, what can we do? Here I have two fractions, the first and the second. The two of it. This is the first, that's the second. So I can add them by taking the LCM, and the LCM clearly is this particular expression. So basically I have to multiply and divide with this particular expression. So me doing that and writing the answer will look like this. So tan of x plus tan of h minus tan of x, and additionally over here we will have into 1 minus tan of x into tan of h, and this entire expression divided with the denominator 1 minus tan of x into tan of h into h, closing the brackets. And now we need to apply the limit. No, before that, a bit of simplification. Sorry, we need to simplify. So we have tan of x plus tan of h minus tan of x plus tan square x into tan of h. I'm just simplifying this, nothing else. Nothing fancy is happening over here. And we have h times of 1 minus tan of x into tan of h. Okay, and closing the brackets over here. So looking for if anything I can cancel, we have plus tan x and minus and nothing else. But in the first, in this case the second and the fourth term, we have tan h that is common. So let's take that out. And you're left out with, let me use small brackets, 1 plus tan square x. What is 1 plus tan square x? Correct, secant square x. So there are quite a few terms getting multiplied and divided. Now for further simplification, see we have look at this. We have something that is related to this. Tan of h divided by h. What is it? Yes, as limit tan of x divided by x, as x tends to 0, it's equal to 1. So what I can do is I can rewrite them. I can rewrite them in the following manner. Limit tan of h by h as h tends towards 0 into limit h tends towards 0. This is secant square x. And this entire expression is getting divided with 1 minus tan of x into tan of h. Now, this is equal to 1. This is not of any particular formula, but I can apply the h over here clearly, because tan of h is 0, so 1 minus 0 is 0, so denominator is not 0, so we are safe. So we can apply the limit. So here we'll substituting, direct substitution, and we have secant square x, this entire thing divided with 1 minus tan of x into 0. So clearly this is 1 in the denominator. So final answer will be f prime of x is equal to secant square x. Now let's have a visual proof. So first thing first, we have two of it, one showing the function and the second showing the derivative. So in this case, we have the value along the y to be minus 4 to 4. Okay, actually it goes from minus infinity to infinity. Obviously, if I show even more than 1000, it won't look good. The graph will not make sense. So I showed it from minus 4 to 4. Now, actually I can show it from minus 10 to 10 at least. That would be okay, I guess. Where is it? This would be a bit better. Yeah. So we can see it moving from minus 10 to 10, while this is moving from 0 to 1, 0 to 10. But of course, this, if I as and when I increase, we can see the slope. It is going from 30, 40, 100. So you can see it is going to thousands, right? So in time, it will go to infinity. You can see that those values, right? So it keeps on increasing exponentially. Of course, in time, it will come down. It will come and touch upon some value, and it's going up. So first thing we need to observe is this graph is always positive. So let's make few observation. The derivative of the function, whatever we are seeing, for this you guys have to be very familiar with the graphs. If not, this won't make sense. Now this is clearly our tan. So this is our tan of x. This is your what? This is a function which is clearly positive, always more than 1 actually. If I zoom in, we can see that it's more than 1. Right? It is equal to and more than 1. Okay? So it is having such a value which is always more than 1. And basically it is to do with positive values. Only positive values is our output. How is this possible? It either is a modulus or a square. So we can see that we have a square over there. Second thing, we can see that at 0 it is 1, and at 90 it's going to infinity. Okay, let me take up those values, 0, 90, and here too again the graph will come in this manner. Let me actually copy this again. This will help. The entire graph will help. Yeah. So we have this to be 0, this to be 90, 180, 270 and 360. So what kind of graph at 0 becomes 1, at 90 goes till infinity, and at 180 again becomes 1, so on and so forth, and infinity, so on and so forth. So clearly this has to be a, yes, inverse of cos, because cos of 0 is 1, so inverse of 1 is 1, while cos of 90 is 0, so 1 by 0 is infinity. Of course here it is minus 1, but because of square it becomes positive 1. So basically we can clearly see that this is related to secant and it is getting squared as well. So that is your derivative of tan x. So this is your graphical view. So now pause and copy everything and copy in this manner.